Students, thank you very much for watching our channel Biopharmaceutics Mentor. Now we have another concept of our second exercise, which is regarding the construction of semi-log graph. I want to explain the difference between the semi-log and the rectilinear. And our common question is why we are constructing the semi-log graph. Whether we have the rectilinear graph, then why we are moving toward the semi-log graph. I want to give you an example of data. For example, when we are calculating the data in our plasma concentration, we have a very big variations. We have some values in milligram per ml and another value is in microgram per ml. And in case of milligram and microgram, we have the difference of the thousand. But when we discussing the difference of the thousand, it means we can't play even plot on the rectilinear graph. So we will have to search another way. That way is the use of the semi-log graph. Once again, I will tell you the uses of the semi-log graph. In case of semi-log graph, we will apply it on the for different uses. For example, if we want to check semi-log graph, it's our today's topic. In case of semi-log graph, why we are saying it's a semi-log? Because it's one side means x-axis is a logarithmic scale, and on x-axis we have the rectilinear scale. On y-axis we have the logarithmic scale. Semi-log graph can be used to check. Okay, for example, if you want to calculate the unknown concentration of drug in plasma. Okay, if we want to check the maximum concentration of drug, if we want to check the area under the curve from the drug, if we check the mean residence time. Okay, if we want to calculate missed dose, and if we want to check Tmax and other pharmacokinetic parameters, for example, bioavailability, bioequivalence, for all these parameters, we have to construct a semi-log graph. So it's very important for our calculations, for pharmacokinetic calculations. Let's start with the word of semi-log. First of all, I would explain the nature of the graph. When you see in our practical exercise book, there are the different ways to construct this type of the graph, because we have a logarithmic scale on y-axis, and there are maybe 1 cycle, 2 cycle, 3 cycle, even 4 or 5 cycle graph. We have the three. For example, we are working on the 3 different cycles of the graph. So we will make it in such a way by constructing this graph. Okay, this graph is basically semi-log graph, and we will write the 1 cycle, cycle 1, 2 cycle, and this is the 3rd cycle. So on, we can make also a 4 cycle graph. Let me clear this graph with the rectilinear, because first of all, if we have any type of the doubt with the structure of this graph, then we can't make it easily. So in parallel, I am making another graph. That graph is basically called rectilinear, and you will feel there is a big difference between the rectilinear and a semi-log graph. In case of rectilinear, we have big boxes, and on x-axis and on y-axis, big boxes of the similar sizes, and inside the big boxes we have small boxes, 10 small boxes in every big box. Okay, we can observe that, for example, here is 1, and here is 0, here is 10, here is say 20, and same case we have similar way of the size. There is 0, 0, 2, 4, and 6. This size of the box is uniform, same, and in this same data shows that number of boxes on x-axis and y-axis are equal to 10. Similar, same size of the boxes. This concept is rectilinear. But when we discuss the semi-log graph, in case of semi-log, we have a different cycles. And by clarifying the cycle concept, we have 10 different areas. Okay, this one, this, and this one. And this is the basic concept of the semi-log graph. We have on y-axis, semi-log graph have this type of the boxes, and at big box we have the 10 equal boxes. You can observe that I have made, for example, I have tried here 1 and then it's a 10, and I want to write 2 here, 3, 4, 5, 6, 7, 8, and 9 and 10. But I have made big difference between the 1 and 2 and very small difference between the 9 and 10, maybe negligible. But in case of x-axis, we have the same, for example, 0 and 2, okay, then another box, and then other box. On y-axis, we are just like to be the similar of the rectilinear. But on x-axis, we have the just similar to the rectilinear. But on y-axis, we have the difference in the scale. And by getting the difference in the scale, we have the values, larger difference between the 1 and 2 and the smaller difference between the 9 and 10. Main reason is when we take the logarithmic values of 1 and 2, we will have the larger difference. And in case of 9 and 10, by taking the logarithm of both, then we will have the smaller difference. So by taking 1 to 10, then 10, then 100, then it's 1,000. One thing we should have to be remembered, in case of semi-log graph, our logarithmic scale means y-axis would never be start with the 0. It would be start with the 1 or 10 or powers of the 10. For example, power of 10, 0 is equal to 1. 10 power minus 1 is 0.1. So we can start here from 0.1, 1, 10, 100, maybe 1, 10, 100, 1,000, difference of the 10. And by taking this type of the concept, we can even cover the whole complete data. Even data have the difference of the thousands, just like I have given you the example. In case of rectilinear, we can't do this, but in case of semi-log, we have the concept to make it very simple by taking this type of the scale. So I hope this concept is cleared for the difference between the rectilinear and the semi-log graph. Now I am moving toward the how to construct it, because it's very much important to calculate the unknown concentration. Okay, if we want to calculate the bioavailability of any drug, then once again we will move toward the semi-log graph. So for this importance, we want to make it very simple and easy to understand for all of you. For example, we will share you the data which is present in our exercise 2 of our exercise book. I will just write the data, then we will move toward its construction of this type of the graph. Okay, we have the data for this of this type in case of class data. So once again, we have both axes just like previous one, y-axis and x-axis, x-axis and y-axis. In case of x-axis, we have 2, 4, 6, 8, and 10. But in case of y-axis, we have 34.5 and then 21.23, then 15.01, then 8.83, and the last one is 6.23. Okay, this is data. For example, we can say this is time and this is the concentration of drug in plasma. Okay, we can write it Cp. So on x-axis we have plasma concentration of drug, and on y-axis we have the Cp, and on x-axis we have a time in hours and plasma concentration in microgram per ml. Now this is the data, and we want to check unknown concentration. For example, we want to check concentration of this type of the drug at 5 hours, then how can we check it? This is our main question. Okay, if we want to check the concentration of drug after getting this injection after 8 hours, 9 hours, every time we can calculate by using this concept. Okay, first of all, construction of this, first of all, the scaling. On x-axis, scaling process is very simple, just like to the rectilinear, because we have the big boxes and small boxes, and big boxes and small boxes have the both have the same size. So we will write here 0, 2, 4, 6, 8 and 10. So these are the lines of our big boxes. Okay, but when we discuss about the y-axis, in case of y-axis, okay, we will see first of all we will observe our minimum concentration and the maximum concentration. Okay, when we see the data, we have the minimum concentration 6.23 and the maximum concentration is 34.5. So we can assume that this data is for the IV injection, because in case of IV injection, we have the decrease in the concentration with the passage of time, because in case of IV injection, only the one process is being occurred, that process is the elimination. So we can assume that having the maximum concentration at the top after 2 hours, and then we will gradually decrease the concentration with the passage of time, because this decrease in the concentration will show us we are just getting the process of the elimination. So first of all, we have to plot 2 with the 34.5. Now I want to make the sometimes the scale. Here is the starting point is 6. Now I will move toward that area, that number which is near to with a 6 but having the power of 10. For example, I have to plot it 6, then the minimum value is 1, because we will never start this type of the graph with 0. So we will start with the 1. Okay, our next cycle would be the 10, 1, 10, then 800, then 1000. We have the data of 34. Then we will once again make another way. Okay, 10 it's 20, then 30, then 40, 50, 60, 70, 80, 90 and 100. Same after 100, when we make the other scale, that would be the 200, then 300, 400, and that cycle would be end at the 1000. And after completing this cycle, when we move to another cycle, that will be start from the 1000, 2000, 4000, 6000, and then 10,000. Okay, now we have the value of 34.5, and we want to make it on from this graph at 2R. We have this one 30. So when we plot it, here is the 30 and 40. So we can write here it's a 34 at 2, 34. Okay, when we move toward that 4, we have a 21. So at 4 we have a 21. Now it's a 24. Okay, at 6 we have a 15. Now if it's a 10, then we can say it's a 15. So we can write here it's a 15. Okay, once again at 8 we have a 8.8. Then 8 we have the less than 10. So we can write here. Okay, at 10 it is a 6. When we interpolate all these lines, okay, remember it's not very much important every point should be at the straight line. It can be or it may be. You have to choose minimum 3 and maximum maybe 12 these points, and then you have to plot the interpolate. And this type of the line, just I have already in my previous video I have shown you the concept of the rectilinear, where we have prepared the inverse data of the straight line. Then we are assuming that their slope would be negative. Once again, in the same scenario would be here, the slope of this line would also be the negative form. But there are some differences. Okay, what are the differences between these? The difference is we have the same equation, y is equal to mx plus b, but now we have taken the graphical graph, that type of having the logarithmic scale. Now we will have to write the equation in such a way. We can use natural log and also can use the logarithmic scale. For example, if we are discussing the logarithmic scale, natural log, then we have ln y is equal to mx plus ln b. Because it's a negative, then we can write the word here minus m. Okay, if we want to using these terms, then we can write ln Cp, because at y-axis we have written the Cp, and in case of m we will write the k minus k, and at the x we have write the t, and plus ln b means we have extrapolated at this value, that value is Cp naught. So ln Cp naught. I have written the word minus with the k because we have decrease in data. Or in case of decrease in data, we have the number of the value of the, or the some symbol of the minus. So, okay, next question is, how can we calculate the k? Okay, time is here, yes. Cp is here, yes. Cp naught is also, by taking the extrapolation of this. Now our main concern is to calculate the k, rate constant, which is actually the slope. Maybe in our previous video you can see the word m. M, K, both are having the same scenarios, but we in pharmacokinetic terms we will use the word K for the rate constant, because this word is commonly using in the every textbook of the pharmacokinetics. So to calculate the K, once again we have to make a slope. Once again, right angle triangle, theta. Now we have delta y here, delta x here, but this delta y is not so much simple, because now we have ln y2 minus ln y1 over x2 minus x1. Okay, in our language, yeah, according to our this graph language, k is equal to ln cp2 minus ln cp1 over t2 minus t1. Remember, in our previous case, we have not taken the natural log. Why we are taking here natural log? Because we have the make the graph of our scale on the logarithmic scale. So ln y2 minus ln y1 is equal to t2 minus t1, or ln cp2 minus ln cp1 is equal to t2 minus t1 is the value of the k. We can have another also equations by using the logarithmic terms. Okay, we can make and this equation by taking the log, that would be log c cp is equal to minus kt over 2.303 plus log cp naught, because you know log is a smaller term and natural log is a larger term. So in case of natural log, when we convert that log into natural log, then we have to multiply this log with the 2.303. Now we have the value of we have replaced this ln with the log, then we have to divide this factor, because this factor has a no log 2.303. This would be the equation for the logarithmic scale. Same scenario, K calculation, Cp calculation, Cp naught calculation. Okay, there is another way to calculate the rate constant K, which I have already mentioned in the book, because we have our concept of ln A minus ln B is equal to ln A divided by B. By applying this concept here, in this equation we can get now ln y2 divided by y1 x2 minus x1. This is another way of to represent the rate constant. So very simple, we can calculate the rate constant. Now our concern is, how can we calculate the unknown concentration? This is very important. By taking the unknown concentration, we have a table. Now we want to calculate the values at 5R. Then how it is possible? Okay, we are writing here T is equal to 5. Okay, K first of all we will calculate by using this. We will get the answer in negative. Then we will write the word here without any type of negative, because negative is present in the example in our equation. So maybe it's a minus 0.2. Then plus ln Cp naught is the value which we have calculated. Maybe it's a 150. Yes. So 150 is the natural log, and ln Cp you can calculate the plasma concentration at 5R by solving this. So this is a very simple concept to calculate the unknown concentration. Now next we will move towards another graph, that will be log graph. Thank you very much for watching. Hope you understand this concept and you have the big idea to calculate the different type of the pharmacokinetic calculations by using the semi-log graph. Thank you very much.